All right, so this is section 10.4, day 2. We're going to continue our idea of how to find area between polar regions. We're also going to introduce in the very last example um, how to find the arc length of a polar curve. We're only doing one example. It's actually a pretty quick and easy formula to use and not too difficult to do. We're going to see if we can do this in one video. We will see it's going to be calculator heavy as far as understanding how these graphs work, because once you get the graphs and understand how it works, the setup and everything is pretty much the same as what we've done in the previous videos. All right, so the area of a polar region between alpha and beta is given by the integral from alpha to beta of 1/2 f of theta squared, or r squared, 1/2 r squared. That's your formula. If you've got to go in between two polar regions, you're going to use 1/2 of r1 of theta squared minus 1/2 of r2 of theta squared, remembering that the first one is the outer one, or the radius which is further away from the pole. So you're always going to take the furthest radius and subtract the inner radius to get the area in between. Okay. And obviously, if you need to sketch the graphs or use your calculator to do the graphs, then that's a good thing to start with. The rest of it we should be able to do by hand. Unless they just can't be done by hand, then we'll use the calculator. All right, so let's go ahead and look at example 1. This one's interesting. Find the area of the region that lies inside the first curve and outside the second curve. R squared equals 8 cosine 2 theta and r equals 2. So the interesting part about this one is that the first curve is not described by r, it's described by r squared, which is definitely going to make it a little bit more challenging to graph. So what we need to do on the calculator here is we need to graph, let's get rid of this, that was an older graph. We need to graph r squared as a positive and a negative square root. So we're going to graph the top part of r as the square root of 8 cosine of 2 theta, cosine of 2 theta. There we go. And then we're going to graph r2 as the negative of the square root of 8 cosine of 2 theta. There are other ways we could have entered that into the calculator. Could have just entered it as the negative of r1 if you know how to do that, which is great. So I'm just going to graph that first. I'm not even going to graph the r equals 2 part so we can see what this looks like. So I'm going to push graphs so we can see what it looks like. So the problem here is that is not the complete graph. And the reason is we actually don't have this thing going far enough. Now, to know how far to go, that's another story. So we need to change our window. Right now, this thing is set to do a theta maximum of 2 pi. Unfortunately, it takes more than 2 pi. I think it's going to take 3 pi, but you might have to play with it just to see. We're going to try 3 pi here and find out. So 3 pi. And I think this should do it. Let's take a look. Nope, not quite. I think we have to go out to 4 pi to do this. The only reason I know this is because I actually know what the graph looks like. It hasn't completed it. And as you can see, the way it pieced it together there, it's pretty interesting. The pieces don't go in an exact, like, smooth order here. And that's partially because of the positive and negative part of the square root. So let's go ahead and put 4 pi in here and graph it. That should complete the graph. There we go. So it kind of looks like an infinity symbol. It's not exactly what it is, but that's kind of what it looks like. And then we're going to go back and we have to graph the second r value, which is just 2. That should just be a circle, so that should show up nicely. Yeah, there we go. So I'm going to go ahead and sketch that. Again, it won't be a great sketch, but I'm going to sketch it on our sheet over here. So we should have, I'm going to cheat a little bit with the circular part. You're going to graph the circle. And then I'm going to graph what looked to be almost like that infinity symbol. Something like that. Not the best, but you get the idea. So what we want to find is the area of the region that lies inside the first curve, which is that infinity symbol, but outside of the second curve. So what we're looking for is this area here and this area here. And you can see the obvious issue here is that this is definitely split. There's no continuity there. It's split into two completely separate parts. So we have to do this by doing separate integration, or what you should notice, and you should have noticed from the calculator, is the symmetry. I can just do the right side and then multiply the whole thing by 2, or even easier maybe, I can do this piece right here and multiply it by 4. So I can just find this top piece right here and then multiply it by 4. That might be the easiest way to do it. So let's do it that way. So we're going to go ahead and solve this for the intersection of the two. Now, the thing is, we're not setting r values equal to each other, although you can. Really, the first one already is r squared, so I'm just going to substitute r equals 2 into r, and what we're going to get is 4 equals 8 cosine of 2 theta. And now we'll solve for theta. So we'll divide by 8. 1/2 is cosine of 2 theta. So we need to set 2 theta equal to the values of cosine that give us a half, which is at your pi thirds. 2 pi thirds. Actually, that's not even a half. That would have to be at 5 pi thirds, because that's where you get positive 1/2, and so on. And then we're going to divide everything by 2. So theta here is going to equal pi sixth, 5 pi sixth, and so on. And what you should be able to hopefully understand is that this is pi sixth. Over here, when you do it this direction, that would be your 5 pi sixth. We're not even going to utilize the 5 pi sixth here, because we're only going to deal with from 0 to pi sixth and then multiply the whole thing by 4. So let's set up the integral. So it should be that the area of this thing is going to be 4 times the integral of 1/2, and we are using the outer one, which is 8 cosine of 2 theta. And before you make the mistake, we are not squaring that because it is already r squared. So I'm not going to square that because it's already r squared. We don't want to square the square because then we're not going to get the right answer there. Minus 1/2. The inner one is 2. Now that is just r, so we do have to square that. D theta. I can factor the 1/2 out to the front. There's actually more that I can factor. We'll deal with that in a second, but we'll take it step by step, which means I'm going to get a 2. Forgot my bounds. This is going to be 0 to pi sixth of the integral from 0 to pi sixth, which leaves us with 8 cosine of 2 theta minus 4. So hopefully technically you see I could factor out another 4 from each one of these things. It's not really necessary in this case, but you could if you wanted to. So now we should be able to take antiderivative. So we're going to have 2 times antiderivative of 8 cosine of 2 theta is going to be a sine of 2 theta. Remember, we have to pull the extra 1/2 out to the front. So that's going to make that a 4, and then minus 4 theta. And we'll evaluate that from 0 to pi over 6. So let's go ahead and plug these things in. The nice thing about the 0 part, once again, it will 0 everything out, so that's good. So we're going to have 4 times the sine of 2 pi 6, which is pi thirds. So sine of pi thirds is root 3 over 2. So we'll have 4 times root 3 over 2 minus 4 times pi 6 is 4 pi sixths, or 2 pi thirds. And then we can simplify and distribute in the 2. And what we're going to get here is, let's see, that's going to be 8 root 3 over 2, which is 4 root 3, minus 4 pi thirds. Okay, and that's kind of the area of the outer part of kind of that infinity type symbol, whatever you want to call it. All right. Second example. We want to find the area of the region that lies inside the first curve and outside the second curve. So the first curve is a cardioid. It doesn't say that, but it is. When we graph it, this is one of the reasons why I want to do this one, because you have to see the graph and it's not easy to tell it's cardioid. Second one is just a circle. That one should make sense because it's a singular angle. It's 3 sine of theta. It should be sitting up on top of the x-axis. So let's get our calculator back out here and go to our y equals. Let's clear all these things out from the previous problem. Oops. All right, so let's graph 2 plus sine of theta. And then we're going to graph for R2, 3 sine of theta. And let's see what these look like. So there's the cardioid, and then there's your circle. Now, the hard part about the cardioid is you really can't see, because it looks really smooth there. You can't see where the little dimple of the heart is, but there is one, and that's part of what causes an issue here. You basically have to do this when using symmetry. You can see that the right half and the left half are symmetric, the top and the bottom are not. So you're going to have to either use the right half or the left half. Typically the right half is easier to use. So when we do this, we're going to have to go from, it looks like negative pi over 2 to pi over 2 using that right half. And we are talking about the area of the region that lies inside the first curve, which is the cardioid, but outside of the second curve. So I don't think I can put anything on here. No, you can't really see it. It's basically the right half of the crescent moon kind of thing, symbol. Hopefully you can see that by looking at it, because I can't really draw on the calculator portion there. So we are going to do an integral. We are going to double it because we're going to use symmetry. From negative pi over 2 to pi over 2. And as a matter of fact, we should double check that just to make sure that that's where the intersection point is. It should be at pi over 2 on the top, but we want to double check that. So let's set these equal to each other. So 2 plus sine of theta equals 3 sine of theta. So we'll subtract sine of theta on both sides, divide by 2. So we get sine of theta equals 1, therefore theta equals pi over 2. So that was correct. The bottom part you should clearly be able to see if we're doing by symmetry. That's where we're going to stop. So that is the correct way to set up the integral. We'll do 1/2 of the outer one, which is going to be your cardioid, 2 plus sine of theta squared, minus 1/2 of the inner one, which is 3 sine of theta squared d theta. So let's go ahead and factor out the 1/2 multiplied by the 2 out on the front. Gets rid of those, which is nice. We're going to have to distribute or FOIL out the 2 plus sine of theta, which is going to be 4 plus 4 sine of theta plus sine squared of theta. Minus, we're going to have to square the 3 sine of theta, which will give us 9 sine squared of theta. D theta. Okay, let's combine our sine squareds so we can do that. So we're going to have 4 plus 4 sine of theta minus 8 sine squared of theta. Hopefully you can already see we're going to have to use the reduction formula to get rid of the sine squared and make that into something which we can take an antiderivative of. So let's do that part. 4 plus 4 sine theta. All right, so the reduction formula for sine squared is 1/2. So that 1/2 times the 8 is just going to give me a 4. And then we're going to have 1 minus cosine of 2 theta d theta. And the last thing we can do here is we can combine our constants. I'm going to try and combine this into one step just to save an extra step of writing here. You should see that I have this 4 here, and when I distribute my -4 into here, I'm also going to have a -4. 4 minus 4 is going to go away. I still have to distribute the -4 into this part, though, so I can't just completely get rid of it. So I'll have 4 sine theta, and then we'll have a plus 4 cosine of 2 theta d theta. Okay, now we can take our antiderivatives and plug the numbers in. So let's see what we get. So 4 sine theta, the antiderivative is -4 cosine theta. 4 cosine of 2 theta is going to be, let's see, what is that going to be? That's going to be a 1/2 cosine, 1/2 sine of 2 theta. The 1/2 times the 4 gives me a 2. And we'll evaluate that from -pi/2 to pi/2. So let's see, what do we get? Plugging in pi/2, cosine of pi/2 is 0. So we get 0 for the first part. Sine of 2 pi times pi/2 is sine of pi. That's also 0. Okay, that whole first part's gone. Plugging in -pi/2, once again, cosine of -pi/2 is also 0. Plugging in -pi/2 into the second part here, something is definitely not right here. Let's see if I can figure out what just happened, because that's also going to give us 0. I think, nope, that looks okay. So I'm still seeing, I'm getting 0 out of all this stuff. So something is wrong. I think maybe it has to do with, let's see, I think maybe it has to do with the way these curves are done. It could be that we have to do the top part of the curve and then the bottom part separately, because the bottom part doesn't really have a second function to subtract from it. It's just the bottom part of that cardioid. Anyway, that's not the intention of the problem. The intention of this problem was actually to have an outside minus inside. And I think one of the main things that I have going on here is I actually have a typo in my problem. It should have been, the first R should have been 1 plus sine theta. So let's just see if we can figure this out. I think that if we do everything the same, except we're going to change this bottom bound to be 0. Let's see if that changes anything. And what that's going to find, I'm going to sketch this on here. What that's going to find with this in particular one, so we have a circle, sits up here like that, and then we have this other thing, which is a cardioid type of thing, which kind of does something like that. By changing it to 0, what we're going to find is this space up here. And then we're going to see if we can just find the area of that cardioid and add those two things together, because this isn't working for some reason. It might have something to do with maybe some tangents at the pole or something. I'm not sure. Let's see if this works. So let's change those things to 0, which we did, which means we're going to change that to 0 as well. Let's see if we get some area out of this, because we should now. Let's get rid of that. So plugging in pi/2 still should give us 0 across the board. Cosine of pi/2, yep, pi. So that's 0 for the first one, minus. Now if we plug in 0 for cosine, cosine of 0 is 1. So that's going to give me -4, and then sine of 0 is nothing. So that does give us an area of the top two pieces. Now it's the top right half and its symmetric side of 4. If we go ahead and do the integral now from, I guess that would have to be from pi to 2 pi, of just the bottom piece, which is just the cardioid, which was 2 plus sine of theta. So 1/2 2 plus sine of theta d theta. In order to not make this video too exceptionally, that should be squared, long, I'm going to pause it and I'm going to come back and see if we have an answer to this and let you know. Okay, so as you can see, I've worked through this a little bit, and this is where we're at. If you need to pause it right there to write some of that down, by all means, go ahead and do so. Let's plug in 2 pi and pi, and we should now have an answer that we can add to our 4. So we're going to get 1/2 of, plugging in 2 pi is going to give us 9 pi, 2 pi, cosine of 2 pi is 1, so minus 4. Sine of 4 pi is 0, so that's the first part. Minus, plugging in pi, we get 9 pi halves. Plugging in pi, we're going to get now plus 4, because cosine of pi is -1, so plus 4, and then sine of 2 pi is gone. So this should simplify. Let's see, we're going to get 9 pi halves, I'm distributing the 2, minus 2, minus 9 pi fourths, minus 2. So 9 pi halves minus 9 pi fourths should be 9 pi fourths minus 4. So if we take that, this is wild, and we add that to the 4 that we got on the top, we're going to get 9 pi fourths minus 4 plus 4, so 9 pi fourths should be the answer. All right, way longer than I intended to spend on that problem, but that should be the answer to our problem. Why it didn't work the other way, I don't know. Nice thing is this last one, it's really just a formula. I don't usually like telling people to memorize formulas. In this case, it might just be the easiest thing to do. We are trying to find the arc length of the polar curve, and the arc length formula is this one right here. It's from alpha to beta, you're going to take the integral of the square root of r squared plus dr over d theta squared, or f prime squared. And that's how you're going to do it. So we will try to find the length of this limaçon. It's a French word. You can graph it. Kind of looks kind of cool if you graph it. From 0 to 2 pi of 1 plus cosine of 2 theta. So you need r squared, which we'll have. We're going to need dr d theta, so let's find that, which is the derivative of r, which in this case is going to be -2 sine of theta, and we're going to plug these things into the integral. So it should be, the length is the integral from 0 to 2 pi, the square root of r squared, which is 1 plus 2 cosine theta squared, plus dr d theta squared, which is -2 sine of theta squared, d theta. I'm not going to tell you this one can't be done by hand, but I don't know how easy it would be, so you're just going to plug that right into our calculator at this point, and we should get the approximation to be 13.364. Some of these might be able to be done by hand using a bunch of trig identities. Some of them might not be. I don't think this one would be an easy one to do. All right, plenty long enough for that video. And sorry about the previous problem as far as the confusion there, but hopefully it all works out.